All right, so 10.5, the last part of our building up the Lotka-Volterra model here. We're just asked to modify the original Lotka-Volterra model by changing this first term, which is our growth rate of rabbits in the absence of foxes, replacing our exponential growth term with this logistic growth model, where as we saw in the last problem, K corresponds to the carrying capacity, and so that's the maximum number of, say, rabbits that my ecosystem could support. And so rather than allowing my population of rabbits to grow uncontrollably in the absence of foxes, we put constraints in place based on the amount of rabbits that that system can actually support. And so what I'm going to do is I'm going to come back over and open up my solution to 10.1. Okay. And so this is just our Lotka-Volterra solution. Okay. And I'm going to save this. Okay, I'm going to call this Lotka-Volterra. Now we're on 10.5. And again, as you solve this, right, a lot of the solution is looking for more qualitative, answers. So the goal of this exercise is, part of the beauty of MATLAB is setting up, you can set up these mathematical models. We can play around with turn knobs, control or change the values of parameters, look at what the effect is on our model. And then here we can, once we can solve, right, we can actually try and improve our model based on, physical intuition and looking at the original terms. And then really it'd be looking at actual data and tweaking to better represent our system. Okay, but anyways, so what I'm going to tweak is this term here. So I'm going to have a new constant k. And so for this problem, we're told to assume a carrying capacity of 150. Okay. Okay. Oop. And actually, what I'm going to do first, okay, is I'm actually just going to run it. Okay, so I can pop my, so it'd be the same as if I ran my function. So I can have 10.1 up. Okay, and let me put that on the side and I'll bring it back. Okay, but now I'm going to add, we said assume a carrying capacity of 150. And so it's this first term in my rate expression for R that changes. Okay, and I need to do a minus. So it's minus A divided by K times R squared. And I'll make these element-wise just to make sure I'm good to go. That's constants. That doesn't really matter, but anyways. Okay, cool. So that's it. Okay, so now what'll happen is, I think before we had like a figure 3 or figure 2, so I'm going to make this figure 3. Okay, so now what happens now is all I did is I defined k, update my rate. So if I rerun this since I had it before, I'll look at the change in behavior. Okay, so before, in our original model, the populations continued to oscillate or fluctuate. So initial population of rabbits, initial population of foxes, right? And they're slightly out of sequence, right? Because as the population of rabbits increases, right, there's going to be more food available for the foxes to eat, which is going to allow their population to grow. But there's going to be an offset in it, right? Once they consume the rabbits, well, then there's actually conversion of rabbits to new foxes. So there's going to be a slight shift, right, in those. Now, when we look at with this logistic growth out to 365 days, is we get fluctuations, but it's like a damped oscillator. So here we have like this oscillatory model. Now we've got essentially a damped oscillator. So you can get fluctuations, but eventually it looks like this is decaying on a constant value. All right, some equilibrium in which you have some number of rabbits at equilibrium with some number of foxes. And the problem makes a comment of, well, okay, that's, and let me close this, right? A lot of this is you making comments. That's solving out to 365 days, okay, 1 year. What if you did 2 years? Okay, so if I do 2 years and I solve it, all right, then it just becomes even more pronounced, right, in that it looks like this value is really becoming constant, right, that you're really reaching some equilibrium. All right, and so it looks like you have about 50 rabbits in equilibrium with about 6 or 7 foxes. So we've got about 50 rabbits, right, in equilibrium with about 7 foxes. And if you were to make this even bigger, right, really, right, it just becomes even more and more pronounced. So just making the slight modification, right? So we used this logistic growth model. Why? Because it didn't make physical sense that the population of rabbits should just be able to grow uncontrollably in the absence of foxes. A logistic growth model made more sense in terms of putting constraints on the number of rabbits that ecosystem could support. When I add that to my dynamic system, so when I bring foxes back in, we actually get this drastically different change in behavior. And even though I have a carrying capacity of 150, right, I never reach that maximum number of rabbits of 150. Right, it looks like we never get beyond, right, that initial value of 100. Right, so even though the carrying capacity is higher, we never reach it. And so that's kind of cool. Small change completely changes the dynamics of my system. So yeah, a lot of the problem was going through and asking yourself some qualitative questions, but hope that helps and makes sense in terms of my solution. Hope you have fun with it, and maybe gain some confidence that you could be a modeler, whether it's ecosystem or modeling other sorts of problems. There we go. Right, we did SIR in class, so you could be a infectious disease modeler, but it's all kind of the same in the same spirit. And let me know if you have any questions.